Alright, what's up guys? In this video, we're going to pick up with some vector calculus, and we're going to be talking about Stoke's theorem again. So we're asked to use Stoke's theorem to determine the circulation of this vector field. So we're in this vector field f here. We got f of x comma y comma z. We got 3y squared I minus cosine of zj plus y minus 2e to the xk. And it's going to be around the square on the xy plane that's defined by what we're given here, r. Okay, R is a region, by the way. So you use Stoke's theorem. So remember, Stoke's theorem is just a higher dimensional version of Green's theorem, basically, or the flux form of Green's theorem. So Stoke's theorem. And remember, Stoke's theorem allows us to relate a line integral to a surface integral, basically. And so Stoke's theorem is just going to be f dot dr is equal to the surface integral. And then we have our three-dimensional curl, remember, which we'll talk about, dot nds. So that's Stoke's theorem. Okay, so let me just point out a couple things about Stoke's theorem, just a couple of things that might look a little funny. So remember, this n here, it's just a unit vector that's normal to our surface S. This is a surface integral. The way you can tell the difference between a surface integral and a double integral is by looking at the differential. So for the surface integrals, it'll be ds. For the double integral, it'll be dA. So I always get that question, how do you tell the difference between surface integral and double integral? Just look at the differentials. And basically what Stoke's theorem says, it basically says that the surface integral of the curl of a function over a surface x bounded by a closed surface, that's why we have that circle on that integral, is basically equal to the line integral of the vector function around that surface. Again, S here is the surface. C is, again, closed curve, and F is the vector field. Now remember, S can be any surface bounded by the closed curve. Okay. And then remember, our vector field F will have continuous first partial derivatives on S. So let me remind you of how to calculate the curl. So there are the two-dimensional curl and the three-dimensional curl. So for the three-dimensional curl, remember, that's just the cross product of the del operator and our vector field. And it's actually not hard at all to memorize the formula, given that you know how to take the cross product. So our unit vectors, I, j, and k, don't change. Okay. And we have our del operator, so that's the partial respect to x, the partial respect to y, the partial respect to z, and then we could say f, g, and h will be our vector field, or components of the vector field, f, g, and h. So that's actually the formula for the curl. And again, if you know how to take the cross product, this formula is easy to remember. I mean, I haven't memorized because I know how to take the cross product. So go back and, check how to find the cross product. I have plenty of videos on how to find a cross product of two vectors. So go back and check that stuff, because you'll need that if you really want to understand how to find three-dimensional curl. It's just a cross product. All right, so that's the formula. Okay, so let's go ahead and do it then. So we know that n here, again, is our unit vector that's normal to the surface. So in our case, okay, n is going to be equal to 0, 0, 1, because it's in the xy plane. So that's what n is going to be here. Let's calculate the curl. So now the curl of f, it's just our cross product. Now, the better you get at this, the less steps you have to write. You might need to make things a little big because you got to stick some information in here. So you might need to make the matrix maybe a little bigger, but So I'm going to just go back to our vector field and stick in the respective components. So this would be 3y squared. This would be minus cosine of z. Pay attention to sign changes too. That can make things a little. And then this would be y minus 2e to the x. And then we just take the curl. Or we find the curl. So let's go get another sheet and do this. So, okay, we know how to do this, remember? So it'll be the partial of x or the partial respect to x for minus cosine z times and then subtract from the partial respect to y for 3y squared. That's if we do k, for example. But if we eliminate the first column and the first row, what we'll essentially have, and I guess I'll break it up a little bit so you guys can kind of see what's happening. So if we break it up, we take out the first column, first row, so we get the partial respect to y, and then we'll have minus cosine of z, and I'm sorry, that's supposed to be the partial respect to z, by the way. And so then we'll have the partial with respect to z, and then this would be y minus 2e to the x. And we just take our partials and we see what we get. Okay, all right, so looks like we're going to get 1 minus sine of z. Okay, so then our I goes out there. Now we take out our second column and our first row this time. So in that case, we got the partial respect to x, and we cancel out that column. So then that means that over here we'll have the partial respect to z, and then we'll have 3y squared, and looks like we'll have y minus 2e to the x. Okay, so in that case, well, if we take the partial with respect to x for y minus 2e to the x, again, when we go through and do this part, by the way, again, all I did was the partial respect to y. Again, we're treating x as constants and you're taking the partial respect to y, so this would be 1. Over here, partial respect to z. Remember that the partial with respect to z for minus cosine z is going to essentially just be positive sine z, because if we take the partial respect to z for positive cosine of z, we get negative sine of z. Two negatives make a positive. Now, by virtue of the fact that we do have to subtract, this will be minus sine of z. So that's why it's not a positive, just in case you were wondering. Okay, so looks like we'll get, let's see, we'll get 2e to the x. This will be minus 0. And then for the last part, we eliminate the third column, first row. So this will be partial respect to x, partial respect to y. Looks like we got 3y squared minus cosine of z. And I'm doing it in small incremental steps just so you can kind of see what's going on. So if we take the partial, well, that's just 0. And then here, we take the partial respect to y for 3y squared. That's going to be minus 6y. And our j goes on the outside there. So this is what we get when we do the curl. We get 1 minus cosine. I'm sorry. 1 minus sine, excuse me, of z. That's I plus 2 e to the x minus 0j plus 0 minus 6y k. Calculate the curl here. Okay, so therefore, we'll get our curl of f. And that's just going to be equal to 1 minus sine of zi. It's going to be plus 2e to the xj. And then this will be minus, remember, 6y k. So that's the curl. Okay, so now we take the dot product. So now we got our curl, and we'll take the dot product of that with the normal vector. So that's just going to be 1 minus sine of z, comma 2e to the x, comma minus 6y. And we'll dot that with our unit vector, which is normal to the surface, which was n is equal to 0, 0, 1, because it was in the xy plane. So that'll be 0, 0, 1. We take the dot product. And notice that this just gives us minus 6y, because this times 0 is 0, this times 0 is 0, minus 6y times 1 is minus 6y, so this just leaves us with minus 6y. So therefore, for the surface integral part, which is over on the right-hand side for Stoke's theorem, when we actually go through, get our curl, take the dot product of that with the unit vector normal to the surface, so we get minus 6y. Okay, so now we go to our surface integral now. And we know the limits of integration because they give us the region. Okay, so this is Stoke's theorem. And we just go through and do all the work that we need to do here. All right, so this now becomes our double integral now. And we got our limits, x between 0 and 1, y is between 0 and 1 as well. And again, we're going to integrate this dy dx because, you know, we have y first and then x second. Now the limits are the same, so it's going to be negative 1 to positive 1, negative 1 to positive 1. And then we get minus 6y. This is dy dx. So now it's just a double integral. So remember, this is just going to be 0, okay, because this is an odd function. We can check that by substituting in a negative y. So if we did f of negative y, that would give us positive 6y. Now, remember, a function is even if, hopefully you remember this. I should have probably did a video on this the other day. Sorry if I didn't. So remember, a function is even if I have if I plug in a negative x, I get f of x. And it's odd if, let's say I do f of negative x, and I get negative f of x. It'll be odd in that case. So in our case, since it was minus 6y, we brought the minus out front, so we would get negative negative f of y is equal to 6y. So then we get f of negative y, which will give us positive 6y. So this is an odd function, so this is just going to equal 0. And essentially, when we integrate with respect to y, since we know we're going to get 0, which is going to get, since it's an odd function, when we integrate with respect to x, which would have been the second double integral, or the second integral we had to deal with as we change to this double integral, we would essentially be integrating 0 from -1 to 1 with respect to x, which is also 0. So the whole thing would just be 0, and that would actually be the answer. So I'll go ahead and write the final answer down on another sheet so you can see it. And I'll post pictures of the solutions here. So we were looking for the circulation in the xy plane. So our final answer, so when we did the integration, again, we had our double integral from -1 to +1, from -1 to +1. We had minus 6y dy dx. That's an odd function, so we just got 0. So that's the circulation. So for the final answer, when we use Stoke's theorem to find the circulation, we end up just getting 0. So the circulation in the xy plane is just 0 based on the work that we did. So notice how we went through, calculated the curl, took the dot product, and that's how we arrived at our answer. So it could be a little bit confusing if you haven't seen a lot of this before. But again, the curl, I kind of broke it up a little bit so you can actually see what was going on. And again, when we took the partials, okay, we get 1. Remember, you're treating the other variables as constant when we're taking partial with respect to y, and then we do have an x. Well, we have y minus 2e to the x, but again, we're treating x as a constant, so that's why it's just 1. Subtract that. Again, just want to reiterate, because a lot of students may ask about this. Remember, the partial with respect to z for minus cosine z is positive sine z, because we know that the partial with respect to z for cosine z is minus sine z. So if it's a negative, that's 2 negatives, make it positive by virtue of the fact that we're supposed to subtract. That gives it minus sine z. So that's where it came from. So I just wanted to clear that up. And then we start over on this side. So that's your answer. And that's how you use Stoke's theorem. So it can be used, and it's just a higher dimensional version of the flux form of Green's theorem, which we talked about in other videos as well. That also helps to find the circulation. So that would essentially be the answer for that. So let me know if you got any questions about it. I'll try to address it. But other than that, I'll see y'all next time.